Hello, and welcome to the video lecture for Topic 7, Atomic Orbitals, Hybrid Orbitals, and Molecular Bonds. Now, at this point, we've been introduced to the concept, or you should have been introduced to the concept of both an orbital and a bond. But really what we need to do is take a look and think about this concept in a bit more detail. So we'll just start off with an orbital, and an orbital is a region in space around an atom wherein we can expect with a certain degree of probability that we will locate an electron, right? And so the electrons that we're primarily concerned with in organic chemistry are the ones that are in the valence shell, the ones that participate in bonding or act as non-bonding pairs, lone pairs on an atom. For hydrogen, the simplest element that we deal with, there is just a single valence shell, which is the 1s orbital. So for hydrogen, right, it just has this 1s orbital, and in its neutral form, it should have one electron. And so what does an s orbital look like? So all s orbitals have the same shape. They are spherical, right? So this is the basic shape of an s orbital, and it can hold up to 2 electrons, right? So if we go then to the next element, helium, it also has just a 1s orbital, and instead of 1 electron, it has 2 electrons. But this is a spherically shaped orbital. You should think of it as a round ball, and somewhere within that sphere of the orbital, we would find an electron. Now, when we move to the next row of the periodic column, the elements that we're going to be primarily interested in this row, are going to be carbon, nitrogen, oxygen, and fluorine, which fluorine will really just be a surrogate for all of our halogens, which we denote as X. So in their valence shell, for example for carbon, we have a 2s orbital that has 2 electrons, and a 2p orbital that has 2 electrons. But we need to break this 2p orbital down a little bit more and take a look at what does a p orbital actually look like. So a p orbital is actually a group of 3 different orbitals that have different orientations along a set of axes. So the p orbital is typically this, what we call either bow tie or dumbbell shape. We have one oriented vertically, we have one oriented horizontally, and then finally we have one oriented such that based on how we're drawing it, one side of that orbital is sticking out of the board towards you, and one side of it is coming behind the board towards me. So here would be that third part of the p orbital, right? And so we designate each of these 3 based on the Cartesian coordinates. So in pink, we have a 2py orbital. In blue, we have a 2pz orbital. And then finally, in green, we have a 2px orbital. Now these assignments of x, y, and z are arbitrary. It's just that each set of lobes needs to have a designation, one of the 3, but we could have picked any designator x, y, or z for any of them, as long as each one gets its own unique one. And what's important to note is that at the very center of all of these p orbitals, in this space here where all the lobes meet, we have a situation called a node, right? So that dot there, that's our node. And what it means to have a node in an orbital is that we know at that point there is 0 probability of finding an electron. So there's no electron density right at that center point. And every time we introduce a node into an orbital, we raise that orbital's energy level relative to an orbital that doesn't have a node. So what would that look like? So for example, with carbon, where we have electrons in both a 2s orbital and we have electrons in 2p orbitals, the energy level of the 2s orbital would be lower than any of the energy levels of the 2p orbitals because each of the 2p orbitals has a node, whereas the 2s orbital, which is spherical, does not have a node, right? So we want to keep this energy distribution in mind as we move through. And so we see with carbon, you have 2 electrons in a 2s orbital, 2 electrons in 2 of the different p orbitals. For nitrogen, if we continue this process, we have 2s2, 2p3. Oxygen would be 2s2, 2p4, and finally fluorine would be 2s2, 2p5. And if we look at the total number of electrons in each of the valence shells, we see that carbon has 4. That means it's 4 electrons short of an octet, which explains why carbon forms 4 bonds. Similarly, moving to nitrogen, we have 5 valence electrons. We're 3 short of an octet. It's looking for 3 more, and so on for oxygen and fluorine. Now, when we move to different rows, our primary concern there is phosphorus, sulfur, and chlorine, if we move to row 3. So phosphorus will have the same electron configuration as nitrogen, except instead of our orbital being at a 2 level, we would have it at a 3 level. So phosphorus's valence shell would be 3s2, 3p3. Sulfur, 3s2, 3p4. And then chlorine would be 3s2, 3p5. Again, only difference between phosphorus, chlorine, sulfur, and nitrogen, oxygen, fluorine is that our valence shell is no longer 2, our valence shell is now 3. 3s orbitals are still spherical, and 3p orbitals are still dumbbells or bow ties, as we see here. So, how can we now use these atomic orbitals to make a chemical bond? Well, if we take a look at the simplest covalent bond we can make between 2 hydrogen atoms, so we'll put 1 hydrogen atom here and 1 hydrogen atom here, their valence orbitals, so each here is now and please use your imagination due to the crudeness of my drawings, but if we imagine that each of these has a 1s orbital with 1 electron in it, we see that when these 2 orbitals overlap, we have created this region here, and this overlap between the 2 1s orbitals is our single bond. And so one of the features that I want you to be aware of is that this overlap that's occurring lies along a line that connects the 2 nuclei. So if I have 1 hydrogen nucleus here, 1 hydrogen nucleus here, we see that that overlap falls along the line connecting the 2 hydrogen nuclei. And so we're going to establish one of our first bonding rules, that orbital overlap that lies along, or that lies, that lies along a line connecting nuclei is a single bond, which more importantly, we want to start now referring to not as a single bond, but a sigma bond. And so we'll use our Greek symbol sigma to describe these types of bond. Any bond where the orbital overlap lies along the same line that connects the 2 nuclei is a sigma bond. So this works. We know that hydrogen, H2, is a linear molecule. Overlap lies along this line, so we just have a single sigma bond connecting these two atoms. And our atomic orbital description is perfectly sufficient to describe what's occurring in this molecule. We can even go so far as to create a situation where we can overlap a 1s orbital and a p orbital. So what would that look like? If we take now, instead of hydrogen and hydrogen, but instead we come to bond a hydrogen atom to a fluorine atom. So here we'll put a hydrogen with its 1s orbital. We'll put in a fluorine. We're going to keep in mind that fluorine is 2s2, 2p5. So here's our fluorine 2s orbital with 2 electrons. Here's one of our p orbitals that'll have 2 electrons in it. Here's our second p orbital with 2 electrons in it. So now we're at 2p4. And finally, our third p orbital with 1 electron in it. We see now that we have the opportunity to form a covalent bond. And if we overlap our p orbital with our s orbital, right, we have now created a covalent bond. 1 electron from hydrogen, 1 electron from fluorine. We're going to arbitrarily say that this p orbital is a 2p z orbital. Our hydrogen orbital is a 1s orbital. But once again, the orbital overlap that we have created lies along the line that connects the hydrogen nucleus and the fluorine nucleus. And so this single bond as well is a sigma bond. And also, conveniently, our atomic orbital view allows us to still explain the geometry of the molecule. Hydrogen or fluorine are connected by a single bond. They are linear. They have a linear orientation to each other. And so our atomic orbital view works very well for us. We're going to take a pause here and take a look at what happens when we try to do this with carbon and hydrogen. So let's try to apply a classic atomic orbital view of bonding to one carbon atom and as many hydrogens as we can possibly attach to it. So we'll begin by just drawing the valence shell for carbon. So here's our carbon nucleus. We have our spherical 2s orbital with 2 electrons. We have our 3p orbitals. Now, if we remember, carbon is 2s2, 2p2. That means our 2s orbital has 2 electrons in it. Our 2px orbital will have 1 electron in it. And because of Hund's rule, our 2py orbital will take the other electron. So our 2px orbital, which we'll put here, has 1 electron in it. And our 2py orbital, which we'll call the vertical one, has 1 orbital in it. If we were to attempt to bond as many hydrogens as possible to this carbon atom as the orbitals are described here, we'd see that we could form 1 orbital or 1 bond with the 2px orbital. And now hydrogen's bringing an electron into this. And we could form another bond with 1 hydrogen atom to this 2py orbital. And here's the electron brought by this hydrogen atom. But there are no other unpaired electrons on this carbon that we can form bonds to, and so this classical view using atomic orbitals really limits us to only making 2 carbon-hydrogen bonds, and would lead us to think that the simplest structure formed between carbon and hydrogen would look something like this. We would have a carbon atom. It would have a non-bonding pair of electrons, which came from its 2s orbital. We would have 2 carbon-hydrogen bonds. And because the p orbitals are at 90-degree angles to each other, we would expect that the bond angle in this molecule should be 90 degrees. At this point, you know that this is the wrong way, that this doesn't happen. We know that the simplest molecule composed of 1 carbon atom and as many hydrogens as possible is CH4. And we know that the bond angles around that carbon atom have to be 109.5 degrees, and that it should have a tetrahedral geometry. So, how can we resolve reality with theory? And the answer is, we need a new theory. And so this new theory that we're going to begin to talk about was actually brought up and developed by a famous chemist named Linus Pauling. Fun fact, Linus Pauling, one of the few people to win 2 Nobel Prizes in 2 different fields. He won the Nobel Prize in chemistry, and then later would go on to win the Nobel Peace Prize as well. And the theory that Linus Pauling came up with is called hybrid orbital theory. And what this theory allows us to do is it allows us to change this classical orbital energy description into something that more accurately represents what we observe in reality. And it starts off with the idea that orbitals of a similar energy level, so for example here, to any orbital in the second valence shell, in valence shell 2, right, that those orbitals can mix together and recombine to make new orbitals that are a hybrid between the different types of orbitals we combined. So for example, for carbon, we can take our 2s orbital and all 3 of our 2p orbitals and combine them together. So we would take 2s plus 2px plus 2py plus 2pz. We combine those together and then redistribute the electron density or the regions evenly and come up with 4 what we call sp3 orbitals. So our electron diagram here for this atomic orbital description changes to become 4 different orbitals of equal energy, each called sp3. And this term sp3 means each of these orbitals is 1 part s orbital character and 3 parts p orbital character, because we took 1 s orbital, 3 p orbitals, combined them together, and then redistributed them evenly. Since now we have 4 orbitals of equal energy level around this carbon atom, we know that based on VSEPR that they're going to need to be evenly distributed around the nucleus of the carbon atom. And we know that 4 regions of electron density have to take on this 109.5 degree bond angle and make a tetrahedral geometry if they're all bonding pairs. One thing that I want to keep, and I want to bring up and keep, and we'll repeat further through this lecture, is since we are combining 4 atomic orbitals, we must create 4 hybrid orbitals. The number of atomic orbitals that goes into hybridization must equal the number of hybrid orbitals that we create. And so since we put 4 in, we have to get 4 hybrids out. So now let's re-examine this bonding of carbon and hydrogen. So we know now we started with an electron diagram that looked like this. Since all 4 of these sp3 orbitals on carbon are of the same energy, we use Hund's rule, and we know that we can put 1 electron into each orbital. So if we start with our carbon atom, we'll have 1 sp3 orbital coming out there. It will have a little tiny second lobe on the other side. We have 1 sp3 orbital coming like this, with a little tiny second lobe on the other side. Remember, that's where its p orbital character comes from, or one way we can visualize it. We'll have 1 orbital coming down like this, with a little lobe. And because now we're going to get overlap of the little lobe from this sp3 orbital and the sp3 orbital that I'm going to draw next, we typically don't include that small lobe when we draw our hybrid orbitals in. And so now there's our 4th hybrid orbital. You can think of this as in plane with the carbon atom, this orbital as in plane with the carbon atom, this orbital out of the board, and this orbital coming behind the board. And keep in mind that our bond angles, or our angles between electron domains, will be 109.5 degrees to give us a tetrahedral geometry. If we look at our electron diagram, we know that each of these orbitals has 1 electron in it. And so now we have 4 unpaired electrons, 1 in each unique orbital around this carbon atom, and we can attach a hydrogen atom at each of these 4 points. Gonna have to do a little erasing here, excuse me. And there's our 4th hydrogen atom. And now we have a true representation, both on an orbital basis, a geometry basis, and a bonding basis for the behavior of carbon when it forms 4 bonds. Now, each of these bonds, each of the regions of overlap, falls along a line connecting the 2 nuclei. Which means that each of these is a sigma bond. And sigma. So we have 4 sigma bonds. Each bond, the overlap lies on a line that's connecting the 2 nuclei. So keep in mind that when an sp3 hybrid orbital, for example on carbon, overlaps with the 1 orbital on hydrogen, this again forms our sigma bond, right? We could also have bonding between 2 different sp3 orbitals that would result in a sigma bond. So there's different combinations that we can use of atomic and hybrid orbitals to arrive at the sigma bond. It could be a 1s and an sp3, it could be an sp2 and an sp3, right? These different types can all achieve a sigma bond. The defining characteristic of a sigma bond is that the orbital overlap lies along the line connecting the 2 nuclei. So now that we've seen the sigma bond and it's allowed us to introduce our sp3 hybrid orbital set, we need to consider a second type of bond, which is known as a pi bond. So a pi bond is a bond that's formed by the overlap of two p orbitals. We're going to just start by taking a look at what that means. So if we take a carbon atom, and here I'm just going to show one of its p orbitals, and a second carbon atom, and one of its a p orbital, we can actually get these two orbitals to overlap side to side. So we would have overlap between the lower lobes down below, and overlap between the upper lobes up above. And we can see that if we draw a line connecting the two nuclei, right, this bond, which has two parts above and below, right, does not lie along that line. It lies above and below it. For this to be able to occur, we must have an unhybridized p orbital on the two atoms that will form the pi bond. All right? This means that our sp3 hybridization doesn't allow us to form carbon-carbon double bonds, or carbon-oxygen double bonds, or carbon-nitrogen double bonds. It doesn't allow us to form any sort of double bond because we used up all three of the p orbitals during hybridization. But that's okay, because we don't have to use all three of the p orbitals for hybridization. This time, we're only going to take the 2s orbital and 2 of the p orbitals and hybridize them together. Keep in mind, I'm using 3 atomic orbitals. That means I'm going to need to generate 3 hybrid orbitals. And since each of those hybrid orbitals is going to be 1 part s orbital character and 2 parts p orbital character, they'll all have the same energy, and this time we call them sp2. This leaves my third p orbital on that carbon atom unhybridized, and it's going to be slightly higher in energy. So I have this 2p orbital left over. Now this energy difference between an sp2 orbital and a 2p orbital is close enough that I can violate Hund's rule, so to speak. Now redistributing these electrons, starting from the lowest energy level, I can put 1 electron into each of the sp2 orbitals, but because the 2p orbital is close enough in energy, I can go ahead and put my 4th electron there without a problem. So let's now take a look at what bonding between 2 carbon atoms using sp2 hybrid orbitals would look like. We'll start off with our carbon atom. And now, even though we have 4 orbitals to work with, we're only going to create 3 regions of electron density because we're going to make a double bond between these 2 carbon atoms. So that means our geometry, we're going to make acetylene, and we see in acetylene that each carbon atom has 3 electron domains, and so that means our bond angles will need to be 120 degrees. So let's start by just putting in our sp2 orbitals. So we'll have an sp2 orbital from this carbon and one from this carbon. We'll have another sp2 orbital at 120 degrees here and here, and then finally one here and one here. Now all of these sp2 orbitals have a very small second lobe on the opposite side of the carbon atom that we typically omit just for clarity. So in pink are our sp2 orbitals. Now each of these carbon atoms still has an unhybridized p orbital on it above equal lobes above and below the carbon atom. Lobe above and a lobe below. Let's go ahead and put our electrons in. So each carbon atom will have 4 electrons, 1 in each of the unique orbitals. So here's one of our sp2, another sp2, third sp2. On our second carbon atom, there's one sp2, another sp2, and a third sp2. And then finally, each carbon atom gets an electron in a p orbital. We already know that we can bring in our hydrogen atoms. So here's a hydrogen atom with its 1s orbital and 1 electron. We've just made a sigma bond there. Here's another hydrogen atom, 1s orbital and its electron. We've made a sigma bond there. We can see that if we draw a line connecting that carbon and hydrogen nuclei, the orbital overlap occurs right along that line, so these are both sigma bonds. Here between the 2 carbon atoms, we have 2 sp2 orbitals, and now these can overlap here. And again, the overlap occurs along a line connecting the 2 nuclei, so we've generated a sigma bond there. On the other carbon atom, here's 1 hydrogen, its electron, 1 hydrogen, its electron, and we have the same scenario as we had here on the right, where we have a sigma bond and a sigma bond. All that's left for us to do is to make our pi bond. So our pi bond is overlap between the 2 unhybridized p orbitals, which occurs above and below the line connecting the 2 carbon nuclei. This now is our pi bond. Half of it is above and half of it is below. So this now explains to us we have 1, 2, 3 regions of electron density. We can distribute that with 120-degree bond angles, right? Our atomic orbital description is not sufficient to do that, but our hybrid orbital description using sp2 hybrid orbitals is. Now this bonding description can be, this sp2 hybrid orbital set can be used for really any of the atoms where we need to create a double bond. So this is going to be carbon, nitrogen, and oxygen that we most frequently encounter. And each of these can take an sp2 hybridization. There's one last scenario we need to look at that we haven't really discussed, and that's triple bonds. So the molecule I'd like to start our discussion of triple bonds with is acetylene. We have a carbon, triple bonded to a carbon, with a single bond to a hydrogen, and a single bond to a hydrogen. The triple bond is actually 3 bonds in one, right? It's a sigma bond, a pi bond, and then a second pi bond. So this tells us that we have to have at least 2 unhybridized p orbitals on each of these carbon atoms. Now, we saw with sp3, we're left with no unhybridized p orbitals. With sp2, we're left with 1 unhybridized p orbital. And so now we have a third hybrid orbital set that we need to create to account for this bonding pattern. One in which we're left with 2 unhybridized p orbitals. And that hybrid orbital set is called the sp hybrid orbital set. It uses the s orbital and a p orbital. And when we mix those two and recombine them, we have to create 2 new hybrid orbitals. So we have an sp hybrid orbital, a second sp hybrid orbital, and at slightly higher energy, we have our remaining 2p orbitals that are unhybridized. Again, we can redistribute electron density, or our electrons in this configuration. One in the sp, a second in the sp, and again, this energy difference between the hybrid orbital and the unhybridized orbital are close enough that we can place one electron in each and still not be violating Hund's rule. So let's take a look at what that bonding pattern now between these four atoms will end up looking like. So I'm going to start again with my two carbon atoms. And I'm going to put in my hybrid orbitals first. So our sp hybrid orbitals need to, or our hybrid orbital situation needs to match our bond angles. So we know here we need to have 180-degree bond angles. And so we'll have one sp hybrid orbital coming off of the back side of this carbon, one off the front. Again, there's a little lobe for each of those that we typically omit. We have another sp hybrid orbital off this carbon and off this carbon. Each of our sp hybrid orbitals will have one electron in it. So there's one electron here, one electron here, one electron here, and one electron there. We have two carbon atoms. Each carbon atom has two sp hybrid orbitals. This is sp, 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 and sp. That leaves for us on each carbon atom two unhybridized p orbitals that we need to account for. And so we'll have one of those two p orbitals above and below the carbon atom. And we'll have one of those p orbitals sticking out of the board and behind the board. And each of those p orbitals will have one electron in it. So here's one electron in our vertical p orbital and one electron in our in and out of the board p orbital. So now let's take a look at the bonds that we've made. Again, just for a reminder, we have a p orbital here, and a p orbital here, and a p orbital there. So now if we look first at our hybrid orbital bonding scenario, we see that we have overlap between these two, between the carbons. It lies along the line connecting those two atoms. So we have a 180-degree bond, so we have here now our first sigma bond. We can introduce a hydrogen atom here at this end. One electron there. We have another sigma bond. And we can finally introduce our second hydrogen atom, our overlap here, and one electron gives us our second sigma bond. Okay, so now we've got our 180-degree bond angles, and we just have to take care of our p orbital overlap. First, working with our verticals, these two p orbitals overlap above and below the plane. So now we've created a pi bond there. And our second set of p orbitals will also overlap behind and coming out of the board. It gets a little messy. And that makes for us our second pi bond. So this now has one region of electron density that has 6 electrons in it between the two carbon atoms. And then we have one region over here, 2 electrons, 180-degree bond angle because we have 2 electron domains. And the same is happening on the other side. And again, we can create an sp hybridization on either carbon, nitrogen, or oxygen. We theoretically can do it with our halogens, but halogens don't engage in double or triple bonding for our purposes in organic chemistry. So really, these are the three atoms where we're going to see any hybridization of sp2 or sp nature. So the last thing I'd like to do here in just a moment is to wrap this up and fill in that table where we started with bond angles and geometries a couple of topics ago, and now start to include hybridization of atoms as part of that picture as well. So before, when we did this table, we only considered the number of electron domains, we considered the bond angle, and we considered what the geometry descriptor was, and we talked about whether they were bonding pairs involved or non-bonding pairs. This time around, we're going to add in a third column of the hybridization. So again, this all starts with the number of electron domains. That will introduce to us our hybrid orbital set that we'll use. It will also determine our bond angles. Our bonding pairs versus non-bonding pairs will then ultimately lead us to our geometry. So, we'll start with the simplest. If we have 4 electron domains, our hybrid orbital set will be sp3. You can also say that the atom that has 4 electron domains around it is sp3 hybridized. The bond angles will be 109 degrees. That approximation is sufficient for our purposes. And depending on the number of bonding versus non-bonding, also we're going to use lone pair here, will tell us our geometry. So if we have 4 bonding pairs, we are tetrahedral. If we have 3 bonding pair and 1 lone pair, we are pyramidal. If we have 2 bonding pairs and 1 lone pair, we are bent. Moving now to 3 electron domains. This will use the sp2 hybrid orbital set. Our bond angles will be 120 degrees. If we have 3 bonding pairs, we have a trigonal planar geometry. And if we have 2 bonding pairs and 1 lone pair, we have a bent geometry. Finally, for 2 electron domains, we will use the sp hybrid orbital set. Our bond angles will be 180 degrees. If we have 2, and I'm going to modify this, bonding domains, we will be linear. Again, this should be corrected here as well. 3 bonding domains. Here we would have 2 bonding domains. So we have two bonding domains we have two electron domains. They're both bonding domains. We'll have a linear geometry. And if we have one bonding domain and one lone pair, we do not provide this a geometry descriptor. Similarly here, in our sp2, if we have one bonding domain and two lone pairs, we do not provide a geometry descriptor. Okay, so that kind of covers an easy way for you to quickly look at an atom, determine its hybridization, its bond angles, and its geometry. If you can remember just this piece, you're going to be in really, really great shape. Definitely being able to then also pull geometry is very useful, but really this corner, this side of the table is by far the most important. So one additional thing, a single bond is a sigma bond. A double bond is a sigma bond and a pi bond. And then finally, a triple bond is one sigma bond and two pi bonds. So if you're asked to, label a bond by how many sigmas and how many pi's does it have, this is what your go-to is. All right, thank you very much. I hope you've enjoyed this video lecture. As always, if you have questions, please feel free to bring them up in conference, lecture, or come by for office hours. Have a great day.